Hello everyone. So today we're going to go over section 4.2, part 2, the second derivative test. So the second derivative test achieves two goals. It supplements the first derivative test for finding local maximum or minimums, and it also reveals the concavity of a function, whether it concaves up or concaves down in different places. So in regards to concavity, given that f prime of c is equal to 0, we can have three different cases. And so these three cases, four graphs, are different functions of x. In the first graph, we have at c a local maximum. In the second graph, we have a local minimum. And in the third case, the next two graphs both have inflection points at c. Okay, let's look at the derivative of each one of the three cases. So in orange here, we have the different derivatives of f of x. As you can see here on the left-hand side of the first graph, the slopes of the tangent line will be positive, so the derivative at those points is positive. And then once we're on the right-hand side, the derivative will be negative. And of course, when the tangent slope is 0 and we have our local maximum, that's when the derivative is equal to 0. And the same examinations hold true for the rest of these graphs. So case in point, here in case 3, we can see that the function is increasing on either side of c. The tangent slope at c is 0. So now we have positive values on either side of the parabola, and at c we have f prime of c equals to 0. Okay, so from there we can find the second derivative. And in the first case, the second derivative would be negative. In the second case, the second derivative will be positive. So that's when the graph will concave up or concave down in the first case and concave up in the second case. Okay, before I go any further, let's summarize those. So again, that is f prime of x is decreasing in the first case. In the second case, f prime of x is increasing. Right, the first was a line with negative slope, the second was a line with positive slope. So what that tells us is that the second derivative in the first case is negative. In the second case, it is positive. And going back to the original graph, we'll notice that f of x concaves down. In the first case, and f of x concaves up in the second case. Now in the third case, notice that f prime of x has a horizontal tangent as x equals c. So that means f double prime of c is equal to 0. F prime of x as a horizontal tangent at x equals to c. So what that means is that, well, we have the function at c neither concaving upwards nor downwards. And that, in this case, gives us inflection points. Okay, so let's talk a little bit more about concavity. Now, our first examination of concavity was about the entire graph. So as we can see here, y equals to x squared, the entire graph concaves up from negative infinity to infinity. In the second graph, the entire graph concaves down, again from negative infinity to infinity. Of course, what is new is that if we have cubic functions like in the third and fourth example here, the first part of the graph concaves down from negative infinity to 0, and then the rest of the graph concaves upwards from 0 to infinity once we're past the inflection point at 0. And of course, the reverse is true, and that is to say it concaves upwards from negative infinity to 0 for the negative x cubed graph, and then it concaves down from 0 to infinity. Okay, so of course we also have concavity for graphs that are not polynomial. So far all our examples have been polynomials. Here we have y equals to square root of x, and you can see that it concaves down from 0 to infinity. And if we have the cube root of x graph like we do on the right, then the first part concaves up from negative infinity to 0, and then it concaves downwards from 0 to infinity. Okay. So how we can use concavity for local maximum and minimum is that if f prime of c is equal to 0 and f double prime of c is greater than 0, then the graph is concaving upwards. And if concaves up, then at c we had a local minimum. And likewise, if f prime of c is equal to 0, making it a critical number, and f double prime of c is less than 0, then the graph concaves down. And that will be a local maximum at c. Okay. So far, we have inflection point that are from cubic functions. So of course there are other inflection points that are possible. The definition of an inflection point is that the point, basically if the second derivative changes sign at c, then c f of c is an inflection point. So the inflection point is an actual point. So when a question asks for the inflection point, this is the expected answer, c, and then substitute substitute c for x in the function and find f of c, and that must be defined. Yeah, so the concavity must change from negative positive to positive negative, which means either f double prime of c is equal to 0 or is undefined, very similar to when we are looking for local maximum minimum and working with critical numbers in the last section. Okay. So these two here are just examples. The one on the left here, the graph is increasing and then it stops increasing for just a moment and then it increases again, which causes an inflection point because, well, it doesn't cause the inflection point, but there's an inflection point there because it changes concavity, concaving downwards to concaving upwards, whereas the graph on the right is actually going from increasing to decreasing um, while changing concavity at the same time. Okay, so let's look at an example here. We are going to look for inflection points of this polynomial function. So in order to find the inflection point, we must first find the second derivative and set it equal to 0. So here we go. The first derivative, we have 4x cubed minus 12x squared. The second derivative, we have 12x squared minus 24x. And if we let that equal to 0 to find x, okay, we can factor out 12x and there are, well, x is either equal to 0 or 2. So the two inflection points, once again, those are points on the original function, and they will be 0, 0. And then we substitute 2 into the original function, and we'll get negative 16 as the second inflection point. All right, so part B asks us to find the interval for which the function concaves up or down. Okay, so the intervals are going to be listed as follows. Well, they're going to be divided by when x is equal to 2. That's one of the stops, and then the other one is when x is equal to 2. So our inflection points. So the intervals really are going to be x is less than 0, and then if x is between 0 and 2, and finally when x is greater than 2. So we can examine whether the second derivative is positive or negative at those points, and then from there, whether the graph is concaving upwards or downwards. All right, so for example, let's say we just need to choose any number that's less than 0. So let's say, for example, negative 3. So if we substitute negative 3 here, we have two negative factors, and then the product will be positive. So this interval actually concaves up. And then between 0 and 2, we can just substitute something like 1. So that will make this part positive and this part negative. And this will be negative as a result, so that concaves down. And choosing any number that's greater than 2, so for example 3, will make both of these parts positive, and once again it will concave up. Okay, so summarize the result. Concave up. That would be from negative infinity to 0, and then from 2 to infinity, and then concave down. That would be from just 0 to 2. All right, and then now part C. Use the second derivative to find any local maximum or minimum. So now if we let the first derivative, and that is 4x cubed minus 12x squared equal to 0, and then we solve for x, so factor out 4x squared, left with x minus 3. So of course that just means that x is equal to 0 or 3. Now we already know that at x equals 0 we have an inflection point, so that's not a local maximum nor minimum. At 3, however, 3 is greater than 2, so it belongs to the third interval from part B. So we know that at x equals 3, the function is concaving upwards. And as a result, we know that this is a local minimum. Okay, and of course, the local minimum is also a point on the graph, so we are to substitute 3 into the original function to find out what the y-coordinate is, and we'll get negative 27. Okay, and there's one more piece. In order to sketch a very good graph that we need to add as well, and that is the original function f of x was equal to x to the 4th power minus 4x cubed. So if we set that equal to 0, and then we can factor out x cubed, get x cubed, x minus 4. So x is equal to 0 or 4, of course, and these are the x-intercepts. Okay. So now we have inflection points, we have the local minimum, and we have the x-intercept. So all this information, and that is to say inflection point 1, 2, and then of course the x-intercept, there's 2 of those, and a local minimum. And also knowing the concavity of this graph, we can draw a very good sketch of the polynomial function, which is just underneath here. And this will look like. So as you can see, just to point out some features here, the concavity changes at 0, 0. It also changes at 2, negative 16, and it reaches the minimum at 3, negative 27, and then moves back upwards to the 0 at 4, 0, or the x-intercept at 4, 0. Okay, so that's how we can use the first and second derivative test to draw a fairly accurate sketch of a polynomial function in this case. Okay, that's it for today, so thank you for listening.